so we've talked a little bit about quantum numbers before, right? And that's when n equals any sort of integer, 1, 2, 3, 4, etc. And this is how close it is to the nucleus, right? We've seen that with the nucleus here and then the circles, right? Where n, this is 1 and this is 2 and that's 3, okay? N represents the level, the base level, where all of these particular types of wave functions occur. It's called the principal quantum number. Or the principal quantum number? Principal. Let's get those two mixed up. Principal quantum numbers. All right. And to put this in an analogy for you, remember that hotel that we talked about? Each one of those floors is going to be a set of coordinates, right? Or a set of or a location. So anything that starts with n is equal to 1 deals with the first floor of the hotel. Anything that's equal to n equals 2 is the second floor, and then you go up from there. Every single point is its own floor, so to speak, as we start building these models going forward, right? Now, that's just the base energy of whatever this structure is. When we deal with the uncertainty that's associated with these things, we talked about de Broglie, right? And we talked about Heisenberg. You have to look at what the overall vision that you get when you look at this structure. So we look at this, and what we have is a circle, and around this circle, because there's a three-dimensional structure, it is no longer a circle. Matter of fact, the shape in this thing is more spherical, right? And we represent this by looking at this and saying how many nodes are present in this particular structure. And then think about this as a balloon. Okay, so I've got a sphere. Are there any nodes in a balloon? No. How do we get a node in there? Well, we take the balloon and we twist it. And we twist that balloon. There's a point where the two pockets of air exist, okay? And that would be a node. But in this case, for the first orbital, our node is going to be essentially 0, okay? And anytime a node is 0, it's always going to be the same shape. And that's that spherical shape. Okay? If I have something where nodes is equal to 1, I've got to represent a shape that's got a pinch somewhere in that spherical structure. Okay? So what we have is a node, a point where there's a pinch, there's sign inversion between each one of the nodes. And whenever we have a sign inversion, we call it plus or minus because it's a mathematical construct. Don't think that there's a charge associated with either top of them. The idea is that this is more of a function of a wave, right? So if I deal with this in a wave, I've got a plus and a minus function. This doesn't have to do anything with charge. It has to do with where these things are located with respect to that line. These things are positive values. These things are negative values. Same thing happens with these nodes, okay? It's not a charge construct. It's just a mathematical construct to indicate that they are different in certain functions, okay, with respect to where their positions are. All right, so if a node is equal to 1, I'm going to have 2 points. If my node is 2, then what I get is I start getting something that's a little bit more complicated, and it's more of a cloverleaf shape. And now I've only got one pinch, but I've got 4 lobes. So as a result, what I end up with are 4 different locations in space. And if you think about this with Cartesian coordinate ideas, you know, you've got one that's plus minus, one that's plus plus, one that's minus plus, one that's minus minus. The same type of general idea, we put into this thing. When there's 2 nodes, we're going to have 2 points of inversion. Okay? Inversion 1, inversion 2. That's where we see that second node. All right? So if I have node 3, things get even a little bit more complicated and associated with that. And I'm not going to bother drawing it, but you can sort of imagine that things are going to they're going to start sprouting more and more of these types of loads. I'm going to have 3 inversions that are associated with it. And they're all from that central point. Why do we use that central point? It's the nucleus, right? If I try to draw this thing, how can I draw it? That's terrible. Okay, that's really bad. So each one of these particular structures, let's see, is there a better picture of this somewhere? Now, even the book doesn't even try to draw this. The book I'm referencing doesn't even try to draw this thing. So I'm not going to try to draw it, but it's a point where we have another type of inversion that goes on there. Okay. Now these nodes that we've got, each one of these nodes has a specific label that's associated with it. Right? When my node is 0, I have a spherical shape. We call these spherical shapes S orbitals. So this is an S orbital. Okay? If I have a node that's 1, this shape, we call this the P orbital. Node 2, okay, these are the D orbitals. And node 3 represents the F orbitals. Can you see that? Yes, you can. All right. Now, node has a special function because each one of these nodes we have to represent it by a quantum number that's associated with it. Okay, and each one of these quantum numbers, in this case, deals with the direction of the shape, kind of. So we represent these things, these shapes, all of these, by the L representation. And this is the angular momentum quantum number. All right? And this means that I can have a value of L that's equal to n minus 1. Okay? And this can be any positive integer. Or any, let me put it this way, any non-negative integer. That's a better way of putting it. Now what does that mean? Well, let's do a couple of examples with this. If n is equal to 1, my L value is going to be 0. Can't have any integers that are that are negative, because that's what we're defining this as. Right? If n is equal to 2, L is going to be equal to 1 or 0, because 0 is a non-negative as well. All right? Okay, so this indicates that not only do I have in N2, I've got the spherical shape, the S orbital, because at this point nodes is equal to 0, but my node all here is also going to be what? And guess what? Yeah, all of these numbers are the L value. So the number of nodes that we have in each one of these descriptors also represents what the L value is. Okay? So if n is equal to 3, at this point, I could have L being 2, 1, or 0. But if n is equal to 4, you got that right. 4, we can have 3, 2, 1, 0. If I have 5, I can have 4, 3, 2, 1, 0. Guess what? 4 exists. Let me put this. 4 has been predicted. Let me put it that way. 4 has been predicted, but it hasn't been proven to exist yet, because when we get to those particular quantum states, the particular nucleus is going to fall apart quite quickly. Yeah, okay. All right. So we've got all of these representations here. Okay. So that's angular momentum. Now let me stop and erase, and we'll keep going from here. Okay. So here is the summary of what we've covered so far. Principal quantum number is n. L, angular momentum quantum number. All right. L, if you use a different book, sometimes you'll run into the term azimuthal quantum number. That's what L has also been called. So it's angular momentum, azimuthal quantum number. Either one of those is going to work for you. Okay? The next value that we're going to do for quantum numbers is the magnetic quantum number. And what the magnetic quantum number is represented as the fun version M. So M is the magnetic quantum number. Okay? And the magnetic quantum number is going to be plus or minus L. Okay. Now what magnetic quantum number is that this tells us the direction of where these orbitals are pointing. Okay? The direction. Okay. So if I look at an L orbital, or excuse me, not L orbital. I don't know what I'm smoking. If I look at a p orbital, okay, and this is where n is equal to 1. So n is equal to 2, L is equal to 1. So this is a p orbital shape. I drew this like that, all right? Now this is a three-dimensional construct, right? So that means that this is the x-axis. I can have an orbital across the x-axis. I can also have an orbital going through the y-axis. Right? Since it's 3 dimensions, where's the other axis? That's right. It's coming out at the board at you. There's another one going behind here. Okay, and that's the z-axis. So I can place these orbitals in 3 locations. The magnetic quantum number doesn't tell us if it's x, y, or z. It just says that there's 3 of them that exist. Each one of them is occupying a specific directional component. X, y, and z. Okay? So magnetic quantum number is plus or minus L. So I've got plus 1 and I've got minus 1. Each one of these is telling me that there's one of them that exists. And I've got 1 here. So x is going to be plus 1 and y is going to be minus 1. How am I going to represent z? What number am I missing? Well, it's an integer range between each one of those. Don't forget that 0 is in the middle of those. Okay? So x, y, and z are all represented there. So whenever I say plus or minus L, in this case, for m being equal to plus or minus L, where L is equal to 1, my m values are going to be plus 1, 0, and minus 1. Okay? If I have a value where L is equal to 2, what are my m values going to be? Alright? So that means I've got plus 2, plus 1, 0, minus 1, minus 2. Okay? So I have 5 directional components for anything that's got 2 nodes built into the system. Okay? What about for L is equal to 3? Well, in this case, m is going to be equal to plus 3, plus 2, plus 1, 0, minus 1, minus 2, and minus 3. Okay? Now, just to throw a bit of a review at you, right, can I have n equal to 2 here? Does the L2 exist when n is equal to 2? You're right, it doesn't. Because if we look back here, L is equal to n minus 1 being a maximum value, and it can't be negative. Okay, so it's the maximum non-negative integer is n minus 1. So if n is equal to 2, this can't exist. So this is an illegal value. N has to be 3 or more in order for the L equals 2 to exist. And n has to be 4 or more for the L equals 3 to exist. Okay? Next video, we're going to talk about a little bit more of the quantum numbers, and we'll do some examples of how to construct these things and what they mean, especially when we apply different rules associated with them.